Good morning, everyone. Let's start today's lecture. Any doubts from the homework? So anyway, I think you're asking about one of the questions where for ethanol, I had asked what is the most effective D1 plus AQ when set to 8 seconds. What should be D1 and what should be AQ? Let's not give the answers because many people have not tried, but I'll give you the approach for it so that will make a little more sense, right? So ethanol is a small molecule. In lecture 20, I actually opened ethanol spectrum, showed you the parameters. The D1 was set to 5 seconds and the AQ was set to 3.27 seconds, if I remember correctly. And the whole question here was, why is a certain number an appropriate choice? Small molecules tend to have a long T1 and a significantly long T2. T2 determines AQ. Approximate half a second of T2 at least should go for 1.5 seconds of acquisition time. If you remember the FID I showed, it was still ringing at 3.27 seconds, right? You could have gone longer. So the basic compromise that comes up when you're setting up acquisition parameters is the fight between resolution and signal to noise. Signal to noise ratio depends upon the signal you have and the noise that you end up collecting based on the acquisition time that you set. If you set a very long acquisition time, unfortunately, your denominator increases, therefore reducing signal to noise ratio. Of course, if you keep a long acquisition time, resolution is quite high. Remember, low magnitude of resolution. So what do we mean by it? Resolution, let us say for an acquisition time of 1 second, resolution is 1 hertz per point. 0.5 hertz per point. Resolution of acquisition time of 3 seconds will be like 0.33 hertz per point. Okay? An experiment that has a low magnitude of this number resolution is called as a high resolution spectrum. Resolution is defined as the ability to distinguish two closely spaced points. Lower the value of resolution, you have a higher power of distinguishing 2 points that are really close to each other. Right? So that's how the resolution is defined. So therefore, as you increase acquisition time, resolution increases. As you increase acquisition time, if your T2 does not help you, your signal to noise reduces. So therefore, the compromise has to be carefully done such that the acquisition time stays between, say, 2 to 3 or 3 to 4 seconds, and you keep a long enough D1 for integration to work out by itself. Okay, maybe I didn't make it clear whether it's a 90-degree pulse experiment or 30-degree pulse experiment. Irrespective of that, keeping a long acquisition time, reasonably long acquisition time and a proper D1 is required for necessary integration. The one more important aspect that would come up here is that if you see the resolution of 0.3 hertz per point is important because the line width for small molecules you're talking about in the range of 0.5 hertz. So if you set your resolution just to 0.5 hertz, lines will still be broader than their natural line width. What is natural line width? Every molecule comes up with its own R2. If you set up your acquisition time too short, let's take this example, then what is going to happen? Your natural line width is 0.5 hertz, but your resolution is 1 hertz. You're choosing to see at a lower resolution. This is akin to the example of seeing a 4K video at 240p on YouTube. You have a 4K option, but you see it in 240p, of course, the resolution is going to be poor, right? So setting up the acquisition time, depending upon the size of the molecule, also matters to get a high resolution spectrum. Okay, so therefore, if you're talking about half a hertz of line width, something slightly less than half a hertz would end up showing the natural line width for molecules. So all that we wanted to emphasize in the last week was to understand and appreciate different parameters that end up deciding the NMR spectrum. Any other questions?
So here also we would need to find the peak properly, we would need resolution twice.
Excellent. We will come to that in the hardware part. What you're trying to define is something called zero filling, okay, or zero padding. I have kept it aside for next week. We'll see how data can still be further processed. I didn't talk about data processing at all. I felt doing quickly 2D this week. We have 3 classes. I want to march ahead with 2D so that you guys will ruminate on the idea of what is two-dimensional NMR experiment. And then when you come back from the break, we can, go towards proteins. That's my plan right now. Okay, if there are no further questions, I hope people once again looked at the video of last lecture or even might recollect what we did in the last class, we took a cyclosporin. We saw the NMR of cyclosporin, and we did appreciate the fact that there are too many protons. With too many proton signals, you have too many resonances within 10 ppm. And in addition, being a small molecule, it also has scalar coupling, which further reduces the resolution. So calling for techniques that are better than just proton 1D NMR to understand how things work out. So in general, as the next immediate step, most of the time, chemists and biochemists would end up resorting to carbon 1D NMR, where you end up doing exactly the same experiment, but you get the carbon 1D. The advantage of this is that depending upon number of carbon atoms, you will get the number of resonances. So for glucose, you'll get 6, and sucrose, you'll start getting 12. And hopefully you can get the assignments for each. Yeah, you didn't have 22 protons as much in sucrose, as much as, you have only 6 carbon atoms for glucose with 12 protons. While you ended up going for 22 protons, you still had only 12 carbons. So number of carbons is still manageable so that you get, and remember, the spectral width for carbon will be around 200 ppm. So you have more resolved resonances, so you'll be able to pick more. So there are some advantages to doing heteronuclear one-dimensional NMR experiment. But going from proton to heteronuclear NMR experiment, from the knowledge that you guys have gained from this class, can anybody tell me what will be the obvious disadvantage of going from proton to carbon? Very good, therefore. Sorry, lower sensitivity implies lower sensitivity. Good. This we have discussed several times. As you reduce the Garamagnetic ratio, the difference between the Zeeman energy levels reduces, therefore the population difference reduces. The population difference reduces, the polarization reduces, the magnitude of polarization reduces, the sensitivity reduces. So therefore, reduced Garamagnetic ratio to lower sensitivity. Any other problems that anybody could perceive?
Low scalar coupling.
No scalar coupling. Okay. So do you do you refer to no scalar coupling as a disadvantage or an advantage?
Depends, I think.
Good. Depends. Exactly. What does it depend on? The advantage would be that you have a higher resolution, but the disadvantage would be that you do not know which carbon is associated with how many protons. So generally, when I talk about carbon 1D, we are talking about decoupled carbon 1D. And therefore, the disadvantage would be you will still get many resonances. You do not know which is CH, which is CH2, which is CH3. Isn't it? So that's the disadvantage. Yeah, it's both an advantage and a disadvantage. Okay. Low sensitivity, in addition to low gamma, is there any other reason?
Natural abundance.
That's right. Good. Low natural abundance. You're talking about 1%. So therefore, in addition to sensitivity going 1/4 from proton to carbon, it'll also go 100 because of concentration. Number of spins decide the sensitivity. Since the number of active NMR spins reduces by 100, you're going to reduce 100. So you're going to go 1/400 of a proton NMR sensitivity for carbon. Okay, so that's yet another problem. There is a way to alleviate it where you C13 enrich your samples. This is commonly done for biomolecules, but the negative is expensive. Okay, so you can still 13C enrich your samples, 15N enrich your samples. But this is slightly more expensive than just getting it at natural isotopic abundance, because you need to isotope enrich whatever nutrients you're giving and then make sure the conversion is as good as you can get, and you get a stably labeled sample. Make sense? What are the disadvantages? We have listed most of it, but anything else? I did say that having no scalar coupling helps improve the resolution. Consider thinking about what is 1 ppm for a proton on a 400 megahertz. So what is 1 ppm for a proton on a 400 megahertz? Louder? 400 hertz. The same thing for a 13C would be 100 hertz. Do you see that within 1 ppm, the higher Garamagnetic ratio can actually pack more hertz, and therefore if you have a certain resolution, if you have 1 hertz per point, you have more points within a certain ppm. Correct? So let's say that we picked something like this for ease of math. Within 1 hertz, you have 2 points, 0.5 hertz per point. So 2 points per hertz. And if you end up taking 1 ppm for both, how many points are going to be there? This will have 800 points. This will have just 200 points. So within 1 ppm, you will have a better resolution in the proton than the carbon. This is the natural way things work due to the gyro-magnetic ratio. So although we said that the chemical shift span is better for carbon, it goes from 0 to 200 ppm, but actually the hertz per point is lesser per ppm for carbon. So if you have multiple carbons that are close to each other, the resolution might not be that high. Okay, so you do take a hit in the resolution. The advantage is that the nature has given you a larger spectral width to span. For instance, you guys should go and check what is the spectral width span of fluorine. Fluorine has a high gyro-magnetic ratio and 19F is close to 100% abundance. This has a span of about 2000 ppm. It's a large chemical shift range. Okay, this happens largely because the nuclei is very sensitive to the electronic environment. And remember, proton to fluorine, what is the difference? The size remains very similar, but fluorine has 7 additional protons that's around, electrons that is around it. So any small changes to the electronic environment will be easily sensed by fluorine than by proton, and therefore spans a much larger chemical shift in terms of ppm. So there are advantages, there are disadvantages. We will worry about disadvantages of having such a large chemical shift window, but let's not go to it right now. Okay, what are we discussing? We are discussing the fact that as your molecular size increases, yes, you can get other NMR, but going from proton to other NMR has its disadvantages. Fluorine is not present naturally in most of the compounds. Amino acids don't have it. Nucleotides don't have it. Is that true? Interestingly, people find that drugs' efficacy increases as you have more fluorine atoms. Okay, that we'll keep it aside. So therefore, it helps people for to screen drugs using fluorine NMR. So we'll keep that away. But apart from that, you are not going to have a situation in order to make sure you'll be able to get other heteronuclear 1D NMR at a high sensitivity, right? There's yet another disadvantage for something like carbon. 13C T1s will be in the range of few seconds. And this is a problem. As the T1 starts to increase significantly, you got to wait for a much longer time for the bulk magnetization to recover to maximize your sensitivity, right? And your T2 times are also short for most of them. So resulting in, very poor situation of the signal dying very fast and the recovery taking much longer, right? So this is not a very ideal scenario. So this is where whatever we learned before MidSim comes to our advantage. What is that? We end up exploiting the INEPT module, which has several advantages. So let me just show the INEPT module in this sense. So if you start from a proton and if you finish from a carbon where the tau is carefully set, what ends up happening is that at the end of this module, you end up generating something of this kind. Okay, the plus minus I leave depending upon the phase here, but it's X or minus X, you're going to have plus or minus depending based on that. Okay, makes sense, right? So what do you end up realizing is that, yes, you are able to generate carbon coherence, most importantly, weighted by gamma of H. So therefore, what are we able to see? If you are able to successfully transfer polarization from proton to carbon, you are able to negate more or less the effects of low gamma. If that makes sense? This can never be negated because the number of 13C you have is going to remain constant. You cannot enrich 13C by doing NMR. You have to do nuclear chemistry to do it, which is not easy to do. So this cannot be negated, but you will still be able to increase the sensitivity about 4 times, 3 to 4 times. Theoretically 4 times, but practically about 2.5 to 3 times is what you end up getting. Okay. And most importantly, even in the case that you have the ability to enrich your sample with C13, doing a proton to carbon seems advantageous because you still get 3 times more sensitivity, 3 to 4 times more sensitivity. Does that make sense? Yeah. And moving on, of course, you can't beat the resolution. If you're still acquiring the carbon, you're still going to get the carbon resolution. This is not going to be beat, but most importantly, if you see this experiment, you are exploiting the bulk magnetization that's generated by the proton spins and measuring carbon information. Therefore, the INEPT module will be significantly driven by the proton T1 times, which are significantly shorter than the carbon or nitrogen T1 times, therefore giving yet another advantage to pulse faster. We also saw in the last week that if you end up changing the flip angle, you can actually pulse much faster, reduce the D1. And similarly, people have played with changing the flip angle of the first pulse in the INEPT and still get better sensitivity per unit time. So far, the advantages of the INEPT module are twofold. One is that you use the polarization from the proton spin. I'm saying proton, it's actually the higher gamma spin, but let's go with proton because we are significantly be driving NMR with proton in biomolecular case. And importantly, the T1 is decided by proton, so therefore shorter D1s. Does that make sense? AQ is still driven by carbon T2. Okay, so that doesn't come in the T2s. If they are short, acquisition time has to be short. But the advantage is that instead of keeping 5 seconds as your D1 delay, maybe you can get away by keeping 1 second to 1.5 seconds, which is a significant increase in repetition times. There's still a small problem with INEPT where you cannot just get done with this because you're going to have an antiphase signal. So what do I mean by it? If you slowly, as we start going towards the stuff, let's say that one of the penultimate density matrix is of the form CX, you'll get a signal like this. The penultimate form is CY, you're going to get the dispersive part. And let's say it's of the form CXHZ with a 2, then actually, let me redo this. This is for carbon decoupled, 13C, 1H decoupled. Okay. In the case that you get a density matrix as CX with carbon proton coupling being present, then the same CX is going to be a doublet. Why is it going to be a doublet? The carbon is coupled with 1 proton. It's coupled to 2 protons, it will be a triplet. 3 protons will be a quartet. Yeah. So in this case, CY will be the same signal but dispersive. Okay, the X and Y are just orthogonal to each other. One is the cos component, the other is the sine component, which is a consequence of the complex Fourier transformation you're doing. Now, if you have something like 2CXHZ, you're going to get a signal of this kind. So let's start naming this. This will be inphase doublet. So this is the case where I am not decoupling. No decoupling. Okay. Yeah. And similarly, if you have something like 2CYHZ, I'm assuming acquisition on the X phase. If you change the acquisition on the Y phase, this will become absorptive, this will become dispersive. Okay, that's the only change that's going to happen. And I'm assuming you're acquiring along the X phase. Why am I saying this? That's for CX square will become 1. CX, CY will still be giving CZ, which will be 0. But take it from me that this is how the signal will look if you end up taking the quadrature. Okay. This we saw already, right? These are just orthogonal to one another. So the important thing that you are able to realize from this density matrix is that although you have been able to improve the polarization from proton, unfortunately, you are developing an antiphase doublet. Why do we have to worry about it? In the case of an inphase doublet, if you end up decoupling, both of this will constructively interfere to give one signal in the middle. But here, if you end up in decoupling, they will destructively interfere to give no signal to you. Does that make sense? So although the INEPT has been useful in reducing the D1 times because it's proton T1s that decides the recycle delay, the problem would be that you still are getting an antiphase doublet which will give you no signal.
Understand the two CHG and two CYHG part.
For now, forget the Y part of it. You have the HZ part that is being present. HZ, if you have a CH spin system, can distinguish whether H is an alpha or the beta state. So in this case, the alpha and beta states, go back to the 4-state energy level diagram that we drew. When we drew the 4-state energy level diagram, you would have had one transition that will be like, say, H alpha C plus minus, and the other will be H beta C plus minus. You remember this?
Yes, sir.
So therefore, if you end up asking, there is no HZ component here. So irrespective of H being an alpha or beta, the C plus minus will be the same signal. This is what we learned earlier in the AX spin system. So now, in addition to that, for these spin transition, if you start asking what is the Z value, the alpha one will come positive, the beta one will come negative, and therefore it inverts the signal, and therefore you get an antiphase doublet. Okay? So go back to the 4-state energy level diagram, figure out the transitions. One will be the alpha transition, one will be the beta transition for proton. Since you're querying HZ in this case, they'll flip the signal of this counterparts. Okay?
So the density matrix that you made there. So when we have the density matrix and we consider relaxation, that's the density matrix we get. So we'll have the relaxation term, we'll have the T2 of carbon also acting there, right?
That's here there will only be T2 of carbon because carbon is transverse. This is slightly more complicated. Different terms, CX, CY will have R2, but CH HZ and CY HZ will not have R2 of carbon itself. It will have some component of R1 of proton also. These relaxation times will be slightly different depending upon the operators that you look at.
A combination.
It will not be a direct combination. It will be some other combinations of it, right? Yes, relaxation would happen. So one point that trying to raise here is that the tau delay is going to cause more relaxation than just the proton 1D experiment. And that's a problem. Yes, that's a problem. But if you go and think about what will be the tau delay for a 1JCH coupling of say 150 hertz, you're talking about something in the period of 3 to 4 milliseconds. Okay, so for 3 to 4 milliseconds, it will not be affected as much. You have signal for about several hundred milliseconds for small molecules. Okay, of course, it's a loss, but then the relaxation loss is coming at a polarization gain. That's why I said you'll never get 4 times improvement. You'll get about 2.5 to 3. Right? I'll come to one other disadvantage for the tau delay, but let's just start with one. One of the major ones is that you have an antiphase term. Okay, let's try to avoid that and come out. So how would you avoid that antiphase term? Is to extend the INEPT with another refocusing term. This also we discussed in the previous lecture before finishing off midsem, where we said, okay, here it's going to be something like 2HZCY, but after another bunch of tau delay, what ends up happening is that you would be able to refocus it, and the 2HZCY at this point will become CX. Go back and do this to convince yourself. Because what is going to happen, since you're applying a tau 180 tau, first of all, the proton chemical shift will not evolve. Since there is a 180 that's applied simultaneously on both, what is going to happen? This product operator will evolve with 2HZCY cos 2 pi j tau minus CX sin 2 pi j tau with a 180 in the middle for the X. So if you set tau to 1 over 4j, then you will only get the CX term. So this is called the refocused INEPT, sometimes called RINEPT. So the problem that we raised, that it's an antiphase term, now got taken care when you made it in phase. Therefore, you can decouple. So one problem taken care of. The other disadvantage of an INEPT, or something that one has to remember, is during the tau delay, relaxation would happen, as fairly raised by a student here. But in addition, the J coupling between proton carbon spans a large range. It spans between something like 125 hertz to 220 hertz, depending upon the CH you're trying to look for. The methyl carbon's proton coupling will be like 125 hertz, but at the same time, a CH in an aromatic system can go up to 220 hertz. Okay, it's the same kind of CH that's being present, and that's going to cause differences in the J delay. So therefore, we'll set the J delay at a compromise of, let's say, at 170 hertz, which is neither methyl nor the aromatic, but both will be a reasonable compromise. Some amount of aromatic will get dephased, but some amount of methyl also get dephased. So you find a reasonable compromise between them to get a proper sensitivity. Okay, it doesn't stop there. There is also one more problem. Remember, CH versus CH2 versus CH3, you will have one J evolution here. The same evolution has to happen 2 times here. The J evolution has to happen 3 times here. Okay, the CH coupling, go back and think about AX, AX2 versus AX3 that you have to do on product operator formalism. The same J coupling has to be evolved 2 times here. The same J coupling has to be evolved 3 times here. So therefore, what is going to happen? The sine term that you have is going to have further terms into something like sine cube of, I'm just giving an idea, 2 pi j tau. So at that point, you know that unless the J is properly tuned, anything that's mistuned will further attenuate the signal. Any number that's less than 1, if you do square or cube, is much less than 1. That's what is going to happen. So CH2, CH3, CH are not fairly treated across this scheme unless you have some other refocusing terms that start to come up. Okay. Now, why did I highlight the advantages and disadvantages of INEPT and RENEPT? Is so that you guys understand how when we move forward, these aspects will be exploited to get carbon data or multi-dimensional NMR data. Okay. So the good thing is that you will get better sensitivity. You can have faster repetition rates. So therefore, sensitivity per unit time can also improve. The negative is that one has to be a little careful that there is going to be relaxation that happens in that tau delay. And also compromise J delays that's not going to improve sensitivity to 4 times as you anticipated, but less than that. Now, that being done, the refocused INEPT unfortunately comes with phase distortions. So when you acquire the spectrum, and the signal should look like this, unfortunately, the signal is going to have some amount of dispersive part. You can never eliminate it even with phase correction. This is a consequence of the experiment. I'm not going to go into the details of it. I request you guys to go and read more about it. So therefore, it causes phase distortions, which results in lowering of sensitivity and lowering of resolution at some point. See, the moment you have antiphase, or rather a dispersive peak, if you have a small positive peak around it, that's going to interfere with it and reduce the signal intensity, isn't it? Right? If you have small positive here, this is going to fight with each other and you see nothing there, then you will count 1 carbon less. That's a problem, right? So in order to alleviate it, this is an excellent example of how, if you understand the theory of some technique, you will be able to come up with very beautiful ways of avoiding problems. So which is where NMR spectroscopists came up with an idea of distortion less enhancement by polarization transfer, because this is called the DEPT experiment, which is going to be a handout, which I expect you guys to go read over the next few days, few weeks. Similar to the fact that I'm writing pulse programs as, pulses and delays. One can also choose to write pulse program this way, where the flip angle is given as 90 degrees and a delay is given as tau or t or whatever. Okay. As always, any small t indicates a variable tau delay, where time delay, while a t or a capital T or tau or something like that gives a constant time delay. How do you determine what is the constant? Do the product operator formalism. You'll find the cos part or sine part with it. You want to maximize one signal versus the other, and therefore you determine or predict what should be the tau delay based on the J delays, J values, correct? So this is a problem where people are trying to look at how does DEPT NMR do better than the refocused INEPT part. Okay, so I'm just going to go over the first few aspects of it. So let's draw the pulse program here. So the pulse program is going to look at like a 90-degree pulse, a tau delay, a 180-degree pulse, and another tau delay, and then an alpha degree pulse. Okay, let me try to, what should I do? I should probably expand it better. I'll change the color. So this is a 90 X phase pulse. This is a 180 X phase pulse. This is an alpha Y phase pulse. Then you have a tau delay. So all these are tau, 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 and tau. And interestingly, in the carbon dimension, you have no pulse until the 180 in the proton comes, where you end up applying a 90 X phase pulse. Then there's a tau delay, and wherever there's an alpha degree pulse, you have a 180 degree carbon pulse. So this is quite different from what we have done in the class, where we generally put the 180s together to get the job done. So this seems a little complicated to start with, but I'm going to walk you guys stepwise to understand what's going on. So what we are trying to understand, how does DEPT help over INEPT, RENEPT rather. Okay, so you're yet again starting with the product operator of, of proton. I is proton here, S is carbon 13. So you're starting with the CH spin system. When you're starting with the CH spin system, you're starting with the density matrix of the I spin, which is IZ. Okay. What is the Hamiltonian that's going to be present? The Hamiltonian has chemical shift parts and the weak scalar coupling part. So far, so good. So this is the entire Hamiltonian is going to exist throughout, except for in pulses. And therefore, and we know what is the Hamiltonian during pulses. We know it's alpha times the phase, right? So we don't have to write the Hamiltonian during those parts. So if you start with an IZ, if you apply a X phase 90 degree pulse, you go to minus IY. At this point of time, you have IY. When you have IY and your Hamiltonian has IZ, SZ and 2 IZ, SZ, the SZ term will not operate at that point because SZ commutes with IY. So we don't have to worry about carbon chemical shift evolution in this tau period, right? And most importantly, in the tau 180 tau period, we have also learned that the proton chemical shift will not evolve during that period. Is that true? Tau period, once again, the proton chemical shift will also not evolve. Fantastic. The only thing that's going to evolve is 2 IZSZ term, which is the scalar coupling. So what do we do here? For one tau delay, scalar coupling is evolved. You cannot evolve scalar coupling for 2 tau delays because you don't have simultaneous 180s on proton and carbon. Only when you have simultaneous 180s on proton and carbon, you could have evolved J coupling for 2 tau delay. Correct? So far, what we are doing is to learn which Hamiltonian is active at which part and only selectively evolving the necessary Hamiltonian. So for the first tau delay, only scalar coupling evolves. I'm not going to tell you how it gets expanded. It's just minus IY cos plus 2 IXSZ sine. And if you set the tau to 1 over, I think 2J, you will end up getting only the 2 IXSZ, which is an antiphase term with coherence along X, I spin. Okay. I'm just taking that up again. Now you have a 180 degree pulse and a 90 degree pulse. 180 degree pulse applied on the I spin, 90 degree pulse applied on the S spin. This is a classic example of how the flip angles don't have to match every time when you apply concomitant pulses in different channels. So you apply those 2 pulses, what is going to happen for I part, it's going to go to minus IX, and SZ is going, no, IX will not change. I'm sorry. Thank you very much. IX, you're applying along IX, it's not going to change, but the pi by 2 along SX will make SZ minus SY. So that becomes minus 2 IX SY. Okay. So now we have reached this part where we have gotten minus 2 IX SY after the 2 pulses are applied. Now, yet again, you have the tau delay. You just learned a moment earlier in this tau delay, IZ will not operate. Right now, you also generated SY, remember. So that's carbon. In this case, SZ should evolve. Remember, in this tau delay previously, you said 2 IZSZ will evolve. From the tau 180 tau, you said, yeah, in this tau duration, only chemical shift got refocused. Scalar coupling will not be. So scalar coupling is still active, right? Go back to the basics that we learned. Scalar coupling and multiple quantum coherence will commute with each other. So therefore, during this tau delay, scalar coupling will not evolve. Does that make sense? Now, the only term that's left out is carbon chemical shift evolution. right? Which should evolve. But if you pay close attention, that's a tau 180 tau. Basically, that will also not evolve. This is a super interesting condition where if you just give a tau delay, you started with minus 2 ix sy, the net effect is literally nothing. Then you would ask, why did we do it? You will see why did we do it later on. Okay, go solve this problem. You'll understand why did we do it. Okay, next aspect that we have, now we have reached this point. Okay, repeat your question. Why not ix is acting on? Iz is acting on?
Ix means I understood this part, sy part.
Yeah, but you had a tau 180 tau to start with, isn't it? This part had a tau 180 tau. We already said during that tau, Iz won't evolve. You're already refocusing based on the previous tau. So at this part, you have the product operator minus 2 ix sy. The density matrix represented as 2 minus ix sy, right? Then you have an alpha degree pulse on I and then pi pulse on x. Sorry, s. So alpha pulse, degree pulse is just going to make it cos alpha and sin alpha component. Since you're applying sy and sy does not change. It just remains. So you end up getting something like 2 ix sy cos alpha minus 2 iz sy sin alpha. Okay. All right. Now that being done, that's because you started from x. You're applying a y phase pulse. You will have x and the z components that come from the I part. Simple flip. So at the end of it, what you also end up having is that you have something like, what am I doing here? Let me see. Okay. Which is equal to only sine part. Okay. I'm going to use one more idea here. So you have two components. What are the two components? You have 2 ix sy cos part and you have 2 iz sy sine part. Do you agree that the ix sy is a multiple quantum term and the iz sy is a single quantum term? And we also said that only single quantum coherences are observable, right? And what is only left in the pulse program is a tau delay. Nothing else is present. Only pulses can change the order of coherence. Okay, only a 90-degree pulse or an alpha degree pulse can change the order of coherence, while a 180-degree pulse will not change, or a tau delay will not change the order of coherence. Therefore, we can happily eliminate this part and not worry about it. Go back and think on what I meant. Only a 90-degree pulse will change the order of coherence. If you're in IZ, it will take you to I plus minus. On the other hand, a 180-degree pulse on IZ will keep it along Z to 0, and this is remain 0. On the other hand, if you have an I plus and you applied a pi pulse along X phase, it will become I minus or minus I minus or whatever, right? So therefore, this will still keep the order of coherence is still 1. It didn't change the order of coherence. So therefore, we can happily neglect the multiple quantum term and only worry about the single quantum term. Okay. Now you take the single quantum term. Now during this tau delay, we already said that the SZ will not evolve. Since you have an IZ term, IZ will also not evolve. So let's not worry about it. The only term that's going to evolve is 2 IZSZ. And when you end up evolving it, you will get the cos and sine pi j terms associated with it. And the moment you end up setting tau to 1 over 2j, you will realize for the CH part, you will only get Sx sine alpha. We have put many things together, but what you are able to realize is that as such a complicated pulse program, you get a very simple final density matrix. And all this means is that if you're acquiring along the Sx axis, you'll only have sine alpha component. Therefore, you have the power of changing alpha to any flip angle to get your signal. Okay. I know this has been overwhelming, but that's exactly why I typed out and gave notes. What I request you guys to do right now is to go back and understand the same thing for CH2 spin system and CH3 spin system. The thing only gets longer because the J coupling has to be evolved multiple times. Go back and think about it. Go back to AX2 system. Otherwise, you just got to calmly sit down and do this. I would strongly encourage everybody to do this as a practice because this tests your understanding of the Liouville-von Neumann equation, the application of it, the Hamiltonian, which commutes with what, and using all those tools, you'll be able to propose or predict what happens. In theory, people did not write the pulse program to get the answer. They wrote the final form and synthesized this experiment rather than, convincing. So this is the power of understanding theory behind how things work. Then you can come up and propose things that don't exist. You can concoct things out of nowhere. Okay. So long story short, the CH2 comes up with, in addition to SX sine alpha for the CH part, it also has a cos alpha part that's being present. When you do the same thing for CH3, you will get a cos square alpha part. So what I'm doing right now, summarizing the CH2 and CH3 parts together. And what you're able to appreciate here, all of them are along SX, which is very good. Therefore, when I acquire, you will not have any phase distortions that come up. And you have the power of changing alpha. What do I mean by it? If you end up plotting the relative intensity, not accounting for 2x of, so this is 1/2 of the signal of CH2, 1/3 of the signal of CH3, then what you end up getting is these kind of oscillations. These are all sinusoidal functions. So the blue one is just sine alpha. The red one is just cos alpha sine alpha, which is nothing but sine 2 alpha by 2, right? And then you have cos square alpha sine alpha, which is the green. And the important outcome that you are able to see here is that if you set your alpha flip angle, so what have you done? You have set everything as a function of alpha. If you set the alpha flip angle to 90 degrees, you will only get the CH spins. CH2 and CH3 will be wiped out. You'll get no signal from them. When you end up setting it to something like 45, you will get CH, CH2, and CH3 all being positive in their magnitude. Basically, DEPT 45, where 45 indicates a flip angle, is very similar to the carbon-13 1D NMR spectrum. Only thing is that quaternary carbons will not be present. Quaternary carbons are one which do not have a proton attached to them. If you don't have proton, you see no signal. So DEPT 45 is very similar to the carbon 1D, just that you're not going to see quaternary carbons. So DEPT 90 will only be CH. On the other hand, DEPT 135, which is 90 plus 45, which nicely comes up here. You would see that CH2 is negative, while CH3 is positive. So quite commonly, what do organic chemists do is to acquire a carbon-13 1D and a DEPT 135. If you compare these two, you would be able to figure out where are the quaternary carbons because they will only come in the carbon 1D. If you end up taking the DEPT 135 to DEPT 1D, CH2s can be immediately distinguished, right? CH3s will anyway have 3 times the sensitivity of CH because there are 3 protons. We'll be able to figure out which is the CH and CH3, although both are positive. And the chemical shifts will also be vastly different. Methyls come around 15-20 ppm, while CHS could span, say, from 10 ppm to 80-90 ppm, or even higher, 120 ppm with an aromatic CH. So this way, what you have learned is that one can end up exploiting NMR spectroscopy and the product operator formalism to understand what will be the outcome of the experiment. The one thing that, once again, I cannot emphasize is that this will be a distortion-less spectrum. Although you would get similar results from an INEPT, here the phase distortions will not exist because when the phase distortions happen, you keep it in multiple quantum coherence when the scalar coupling does not evolve. That's the smartness of this experiment. I can't go into the details of it right now, but the major aspect that comes up here is that across the different terms, you would see that the multiple quantum term is how you save the signal so as to not result in phase distortion. Because in the signal is in multiple quantum term, the scalar coupling does not evolve. Thank you very much, everybody.